In this video, I'm going to talk about how co-channel interference destroys microcell throughput. It's the first of a series of videos that answers the question, what is it about microcell wireless LANs that have made so many wireless LAN administrators and end users unhappy and frustrated? It's an important question because microcell, even though it's a first-generation wireless LAN architecture, is still used by most of the leading enterprise wireless LAN vendors today. And a lot of people are unhappy with it. We at Extricom know that because we hear about microcell issues all the time from customers who have switched over to our architecture. The biggest problem with microcell is called co-channel interference. Co-channel interference can simply destroy microcell throughput, reducing data traffic to a crawl. To understand why, let's digress a bit and talk very briefly about what a microcell is and what co-channel interference means. In a wireless LAN, when any client device, such as a laptop or voice over IP phone, is sending or receiving data, all of the other devices in the area must wait. That's a lot different than the cellular networks that we are familiar with. In cellular technology, there can be many sessions in progress simultaneously inside a single cell. But not in wireless LAN. In a wireless LAN standard data communication, only one end-user device in a cell can communicate at any given time. Consequently, the early designers of the wireless LAN standard 802.11 realized that to get reasonable bandwidth from a wireless LAN deployment, there must be several small cells in any given area, like this. That's why this architecture is called microcell. Each cell would operate on a different frequency, so a communication in one cell would not disrupt communication in another cell. So in theory, with this architecture, there would be several data wireless LAN conversations happening in parallel, one per cell. Now let's take this concept into the real world and cover the first floor of a school or office with wireless LAN. We'll need about 9 cells. Looks good, right? Well, not in reality. At the wireless LAN frequency band of 2.4 gigahertz, there are only 3 non-overlapping channels, 1, 6, and 11. So that means that our 9-cell deployment actually looks like this. Take note that the cell channels have started to repeat. You can see, for example, that cell 1 is repeated 3 times, and that's the same for cell channel 6 and the cells that are also on channel 11. So now we have several cells on the same floor that use the same frequency. Now you might say, so what? The diagram looks okay. Each cell is distinct and does not interfere with the others. Well, here's the problem. In reality, the cells actually overlap quite a lot. The cell boundaries are highly overlapping, and there's quite a lot of interference between the various cells. Now we have to get a bit technical to explain why this is the case. Microcells are often placed close together, about 10 to 20 meters from each other, because we don't want to crowd too many clients into any given cell, because as we said before, only one communication can take place at a time. Also, having a spacing of about 10 to 20 meters ensures that the clients get higher data rates. Now here's the problem. The RF energy that the APs and the clients emit doesn't just travel 20 meters. In the average environment, it travels several hundred meters, as shown in the diagram that we're looking at right now. At the low signaling rates that are used by APs and clients to determine who can transmit, this RF energy is heard hundreds of meters from the transmission point. So for example, let's take a look at the channel 11 cells now. when AP3 signals client 3, the AP5 cell and the AP7 cell, here the transmission must wait. The same effect happens to the channel 1 cells, which are in white, and also to the channel 6 cells, which are colored gray. So in our example, instead of the throughput of 9 cells, now we're effectively back to where we started, with a throughput of 3 cells, or actually even lower, as devices and APs fight for airtime and retries fill the air instead of actual data. So to conclude, instead of getting more bandwidth for each microcell AP you add, just the opposite is true. The more APs you add, the more co-channel interference you get, and let's just say that things can get ugly. In the next video, I'll talk about how Extricom's solution gets us out of this situation.